To understand matter at the atomic level, chemists need a way to map the precise architecture of molecules without destroying them in the process. Nuclear magnetic resonance, or NMR, solves this problem. It allows researchers to deduce exact atomic configurations strictly by probing the magnetic properties of the nuclei within a sample. Today, the user experience of this technique is remarkably streamlined. A technician drops a sample into a monolithic, liquid helium-cooled superconducting cylinder, like this Bruker 400, types a command into a computer, and waits for a highly detailed readout. But the sleek exterior of modern instruments masks an incredibly complex physical architecture. The original classical spectrometers required precise physical manipulation of magnetic fields and radiofrequencies to prise structural data out of a molecule. To understand what those final data readouts actually mean, we need to open the black box. We are going to logically engineer an NMR spectrometer from the ground up, starting with the basic quantum physics of the atom. The physical bedrock of NMR relies on a specific quirk of quantum mechanics. Nuclei with odd mass numbers, like hydrogen-1 or carbon-13, possess both an electric charge and mechanical spin. Because any spinning charge generates a magnetic field, these specific nuclei act exactly like tiny bar magnets. When you place these tiny magnets into a strong external static magnetic field, which we call H0, they do not simply snap into static alignment. Instead, the interaction between their spin and the external field causes them to move in a characteristic circular pattern. It is the exact same gyroscopic motion you see when a spinning top begins to wobble under the influence of Earth's gravity. The top spins on its axis, but that axis slowly sweeps out a cone. In physics, this is known as precessional motion. The rate of this wobble is defined by the Larmor equation, omega equals gamma times H0. Gamma is the gyromagnetic ratio, a fixed constant for any specific type of nucleus. Because gamma is constant, the equation reveals a strict linear relationship. The precessional frequency of the nucleus is directly and purely proportional to the strength of the applied magnetic field. Increase the field strength, and the nucleus wobbles faster. This equation is the operating manual for the entire machine. The entire engineering challenge of NMR is simply designing hardware capable of measuring this precise precessional frequency, because that frequency contains the exact chemical environment of the atom. Our first hardware requirement is the main magnet. To control the right side of the Larmor equation, we need to generate an intensely stable and perfectly homogeneous magnetic field across our sample. If the field is uneven, the system fails catastrophically. Nuclei in the top corner of the sample would experience a slightly different field strength than nuclei in the bottom corner. According to our equation, they would precess at slightly different frequencies, producing a smeared, unreadable signal. Engineers solve this physical limitation mechanically. They place the sample in a highly precise, narrow glass tube, usually 5 millimeters in diameter, and spin it rapidly on its exact vertical axis. This physical rotation averages out the spatial magnetic anomalies, forcing all parts of the solution to experience a uniform field. But the sample itself requires specific preparation. We have to dissolve the chemical in a solvent that lacks its own interfering protons. Deuterated chloroform is the standard choice, as its heavy hydrogen isotope doesn't overlap with normal proton signals. We also add a trace amount of tetramethylsaline, or TMS. Because the protons in TMS are highly shielded, they produce an extreme signal that researchers use as an internal standard, an absolute 0 point on the frequency scale to measure all other shifts against. Only after achieving this perfectly uniform magnetic environment, through both hardware alignment and chemical control, can the actual measurement begin. Measurement requires us to achieve resonance. We have to hit these precessing nuclei with electromagnetic radiation that exactly matches their precessional frequency. When the energies match, the low-energy nuclei absorb the radiation and flip their alignment to a higher energy state. To deliver this energy, we install a radiofrequency transmitter coil. Notice that it sits strictly perpendicular to the main magnetic field to ensure the waves interact properly with the spinning nuclei. Here is the central complication. Even under a uniform external magnet, protons in different parts of a molecule experience different local magnetic fields caused by their surrounding electrons. These electron clouds act as shields, meaning protons in different chemical environments will precess at slightly different frequencies. To map these variations, classical instruments use a continuous wave, or CW, setup. Instead of constantly tuning the radio transmitter to hunt for different frequencies, engineers hold the RF source perfectly constant, often at exactly 60 MHz. To find the nuclei, they manipulate the other variable in the Larmor equation, the magnetic field. They install a sweep generator, which supplies a variable DC current to a secondary, smaller set of magnet coils. The sweep generator slowly and continuously ramps the total magnetic field up or down. As the field strength changes, the precessional frequency of the sample changes. One by one, different groups of shielded protons are forced into resonance as their specific frequency perfectly aligns with the constant 60 MHz broadcast. Continuous wave NMR is a sequential scan. We are intentionally changing the variables of the Larmor equation mid-experiment to isolate and flip specific chemical environments, one fraction of a Gauss at a time. To capture the exact moment these protons flip, we add the final hardware component, the receiver coil. It is positioned perpendicular to both the main magnetic field and the RF transmitter. When the precession frequency is matched, the nuclei flip over. This sudden change in magnetic flux induces an electromotive force, a tiny electrical current, directly in the detector coil. This microscopic signal is instantly amplified and sent to a recorder, which plots the strength of the resonance signal against the precise strength of the magnetic field at that exact millisecond. This is an illustration of a real classical output peak from a CW scan. Notice the distinct decreasing series of oscillations immediately following the sharp peak. This is an artifact called ringing. Ringing occurs because the sweep generator continues to increase the magnetic field, but the recently excited nuclei take time to relax back to their equilibrium state. They continue to emit a rapidly decaying signal that interferes slightly with the ongoing scan. While it looks like an error, ringing is highly desirable. It indicates that the excited nuclei are relaxing uniformly, which proves that the main magnetic field is highly homogeneous. It confirms the CW hardware is operating flawlessly. The continuous wave method is precise, but scanning frequencies sequentially is incredibly slow. For a weak, rare isotope like carbon-13, a CW scan simply takes far too long to capture a usable signal. To solve this, modern NMR dropped the sweep generator entirely, transitioning to the pulsed Fourier Transform method. Instead of a steady sweep, an FT instrument fires a single, incredibly powerful radiofrequency pulse, covering a wide band of frequencies all at once. Because the pulse spans such a broad frequency range, it satisfies the resonance conditions for every single magnetic nucleus in the entire molecule simultaneously. When the pulse turns off, the receiver doesn't pick up a single group of protons. Instead, it captures a massive chorus of every nucleus precessing and relaxing simultaneously. The resulting current is a highly complex, interfering waveform. This graph illustrates that raw output. It is called the free induction decay, or FID curve. As you can see in the time domain graph for acetone at the top, it is a wildly oscillating signal that decays rapidly as the nuclei lose their energy. FT instrumentation trades a simple, sequential scan for a highly complex, composite signal. Every piece of chemical data in the molecule is captured in a fraction of a second, but it is entirely overlaid upon itself. The free induction decay is incredibly data-rich, but it is completely unreadable to a human chemist trying to identify molecular structure. To make use of FT-NMR, the spectrometer requires an integrated computer processor capable of handling intense mathematical operations. The computer's Fourier Transform breaks the complex time domain FID into individual sine and cosine waves, converting time into frequency. Each isolated frequency maps a specific chemical environment. Plotted on a standardized chemical shift scale, it yields the distinct peaks chemists use to deduce structure. The machine loop is absolute. The massive magnet aligns spins. The RF coils manipulate them, and the math decodes them. The modern NMR spectrometer isn't a black box out of convenience. It operates exactly as it always has. It is the ultimate engineered optimization of